In early 1941, British planners worked through uncomfortable lists. On paper, the shortages were plain. Britain was critically weak in anti-tank guns. Modern pieces were held back for the regular army. The Home Guard, raised to face a possible invasion, had almost nothing that could threaten armour. Invasion remained a real planning assumption. If German tanks came, scattered infantry units in villages and small towns would need anything that might slow them down. Procurement officers, under pressure and short of time, opened the door to private proposals, improvisations, and unorthodox ideas. Into that atmosphere of scarcity and urgency came a weapon that looked more like a pram than a gun, the Smith gun. It took its name from its inventor, the Reverend William H. Smith, and he proposed a smoothbore bomb-throwing weapon that workshops could build quickly with minimal machining. Its carriage did not resemble a conventional gun mount. It looked like a small civilian baby carriage. Two-spoked wheels held a short, stubby barrel between them. A tubular axle linked the wheels and the barrel. In this form, the gun could be towed behind a small car or manhandled by a Home Guard crew over short distances. In travel mode, the barrel lay low between the wheels, giving it a pram-like profile. There was no split trail extending behind it and no separate firing platform with spades. Structurally, the axle and wheels carried almost everything. Elevation, traverse, and basic stability depended on the wheel layout. This immediately set the Smith gun apart from orthodox field pieces, and its most distinctive feature appeared when the crew prepared it for action. To fire it, they tipped the gun sideways. One wheel was lifted clear of the ground. The other wheel stayed down and became a circular firing base. The barrel, now offset, pointed diagonally upwards from the axle. In that position, the rim of the grounded wheel acted as a makeshift baseplate, taking recoil and weight. The raised wheel did nothing once the gun was in this stance. The result was a one-legged mount, functional but inherently awkward. On paper, this offered a clear advantage. Because the entire gun sat on a single-wheel rim, it could be rotated around that point. In theory, this gave the Smith gun full 360-degree traverse. The crew could pivot the whole assembly on the grounded wheel to follow a target. An elevation was handled by a simple hinged joint near the trunnions. There was no equilibrator and no complex recoil buffer. Recoil travel was short and effectively unbraked, transmitting force directly into the wheel and ground. Depending on whether the soil was hard, soft, dry, or wet, the rim either skidded or bit into the earth, sinking more deeply in some conditions than others. The barrel was roughly 3 inches in caliber, smoothbore, and relatively thick-walled. The intention was to keep machining minimal and rely on mass rather than fine tolerances. The breech was a straightforward hinged breech block carrying a firing pin assembly. Propellant charges were loaded behind the projectile. The Smith gun used ammunition from the existing 3-inch mortar family. It could fire high-explosive bombs and dedicated anti-tank bombs, and giving it a dual role from the outset. The anti-tank bomb was a shape-charged design. Its performance depended on standoff distance and reliable fuse function to form an effective jet against armour. The smoothbore barrel gave the projectile almost no spin. Fins on the bomb provided stability in flight. Even so, its effective range for anti-tank work was short. In practice, it was a close-range ambush weapon against armour. Against infantry or field positions, it could lob high-explosive rounds like a light howitzer. This dual use attracted interest during early evaluations. Manufacturing proposals were built around practicality. Mild steel was specified wherever possible. Critical components received selective heat treatment when facilities allowed, but the weapon had to be producible by firms without advanced machine tools. Forging and precision machining were reduced where they could be. Welding replaced heavier manufacturing processes. Simplified jigs held barrel and axle in alignment to an acceptable standard. Ordnance officers drafted inspection protocols quickly, leaning on existing mortar-proof procedures. Again and again, decisions favoured speed and quantity over refinement. In early trials, the Smith gun did not look entirely foolish. Some observers were impressed by what it seemed to offer. On the road, it took up little space. It could move along constricted lanes where larger pieces would struggle. 2 men, at least in theory, could deploy it without a vehicle. Once tipped up onto the wheel baseplate, its profile stayed low, useful in the hedged landscapes of much of Britain. On paper, and it looked suited to narrow country roads and village approaches. On paper, it could be emplaced quickly and stored easily in small depots. Reality was less forgiving. Every claimed advantage came with complications. The tipping drill turned out to be demanding. Getting the gun from travel mode onto the single grounded wheel required coordinated effort. Undertrained or out-of-practice crews found the weapon tended to shift unpredictably during the rotation. On hard surfaces, the grounded wheel could skid instead of settling. On softer ground, the rim might bite too deeply on one side, putting the gun off balance. If the wheel did not seat correctly, the firing position was unstable. Training manuals therefore prescribed a strict step-by-step deployment drill to keep the movement controlled. Regulations set a minimum crew of 3. One acted as commander, supervising and giving laying instructions. Another worked the breech and loaded the bomb. A third handled traverse and elevation between shots. Extra men could help with ammunition and movement. Each role had defined safety checks before firing. Drills covered misfires, partial extractions, and recovery procedures. The amount of procedure contrasted with the weapon's supposed simplicity. In the Home Guard, training time was uneven. Some platoons had regular access to ranges and could drill properly. Others met only intermittently in the evenings after civilian work, with little chance for extensive live practice. Attendance depended on factory shifts and shop hours as much as military need. Handling skills varied widely between counties. Units with ex-artillerymen, engineers, while more pre-war territorial gunners adapted more quickly. Detachments without such experience relied heavily on pamphlets and diagrams. That gap later showed in accident statistics and in the stories men told about the gun. Ammunition supply brought its own technical constraints. High explosive bombs used thin-walled cast bodies. Their fuses were drawn from patterns already used in mortars and howitzers. Detonation reliability depended on impact angle and target hardness. The anti-tank bombs carried a shaped charge liner and explosive filler that demanded precise fuse timing and stable flight. Incorrect fuse settings could produce low-order detonations. Poor storage conditions could degrade propellant and explosives before they were ever fired. On paper, ordnance officers called for tight propellant tolerances. In wartime production, the batches inevitably differed. Minor variations in propellant burn characteristics produced noticeable changes in refuse coil. Some barrels saw higher internal pressures than design figures had anticipated. Steel margins built into the barrel tolerated limited overpressure, but not indefinitely. At the same time, breech fittings sometimes loosened under repeated firing. Thread wear and imperfect assembly made these problems worse. Inspection teams lacked the manpower to monitor every distributed Home Guard weapon regularly. At the ranges, ballistic performance was mixed. Against stationary practice targets, accuracy was just about acceptable. Against moving tank silhouettes, hit probability dropped sharply. Crews had to judge range precisely under pressure, and little in the design helped them. The sighting system was rudimentary, with only coarse graduations. Optical sights were omitted to save cost and complexity. Crews therefore depended on experience and repeated live firing. Few Home Guard units had enough time, ammunition and range access to reach that level. At very short ranges, the anti-tank bomb could perform as intended. Older armour and light vehicles were vulnerable if they came too close. Against newer German front armour, the effect was much weaker. Even so, planners saw a role for the weapon in flanking or close-range ambush. Placed near road bends, gates and choke points, a Smith gun might still deliver a damaging side shot. Concealment rather than range became the key. In that respect, it fit the Home Guard's defensive doctrine of lying low and striking at close distance. It was never designed for long-range exchanges across open ground. Though logisticians appreciated one clear advantage: the guns stored well. In transport sheds, Smith guns could be parked side by side without long trails. The baby carriage layout cut overall length. Without a trail, packing and stacking inside limited spaces was simpler. On firm ground, the wheels allowed for quick relocation. On grass or in mud, moving it became harder work, especially for small crews. Tyres, wooden or rubber, behaved differently on different surfaces, something depot manuals tried to address with recommended routes for local defensive plans. Production was spread across several engineering firms. Some concentrated on barrels and breech mechanisms, others produced axles, wheels and structural parts. Smaller workshops supplied brackets, pins and adjustment components. Subcontracting increased output but complicated quality control. Tolerances could drift between batches from different sources. Central inspection stations tried to enforce uniform standards. Their staff and facilities, however, were always chasing a production rate set by wartime demand. Metallurgical problems appeared early. Investigators saw axles failing under repeated shock loads, breaking in ways that suggested brittle fracture rather than slow fatigue. Tracing these failures back, they found inconsistent heat treatment procedures and variations in steel composition from different mills. Cooling rates during quenching differed between batches. Residual stresses built up where the metal's geometry changed sharply, around threads, shoulders, and joints. Cracks often began there at stress concentration points. Her revised specifications tried to reduce these concentrations by smoothing transitions and modifying details, but such changes took time to reach production. The wheel rims also carried more than the gun's weight. They had to be rigid enough to serve as a firing base. At the same time, they still functioned as wheels. If made too thin, they deformed locally under recoil, changing how they met the ground. If made too thick, they became heavy and harder for crews to handle. Compromise dimensions were agreed in hurried design meetings. In the field, actual loads often exceeded design assumptions. Repeated firing worked spokes loose or pushed the rims out of true. Correspondence records debates about barrel wall thickness. Thicker walls made for safer barrels but used more steel. Thinner walls saved material and increased the number of barrels per allocation. War Office officials walked a line between quantity and robustness. Some argued that inexperienced Home Guard crews needed generous safety margins. Others insisted that arming more units was the priority. The final drawings captured a compromise reached without lengthy testing. Later accidents brought those earlier tensions back into focus. The tipping procedure carried physical risks. To get the gun into firing position, crews had to lift and rotate a heavy mass. Slips in footing or poor grip could strain joints or cause falls. If they lost control, the weapon might crash down, damaging spokes, sights, or the breech. Training films showed a slow, deliberate rotation onto the rim. On wet grass, gritty tracks, or rubble, practice rarely matched the ideal. Once firing began, recoil behavior varied with the surface. On compacted soil, the rim usually skidded slightly and then settled. On concrete, it could bounce or twist. On sand or very soft ground, the wheel might dig in and tilt the gun. Even mild tilt changed elevation and traverse between shots. Crews often had to relay after each round, reducing effective rate of fire. Fatigue grew as they repeatedly adjusted and manhandled the unstable mount. Loading also demanded care. Bomb fins extended behind the main body. Hurried handling could bend fins while crews tried to maintain rate of fire. Bent fins caused instability in flight. An unstable bomb might yaw or strike armour at a poor angle. Such impacts reduced fuse effectiveness and distorted shape charge performance. The maintenance instructions told crews to inspect fins before loading. Under time pressure, that level of attention often slipped. Fuses tried to balance safety and function. Setback forces during firing were meant to arm them only after the bomb had left the barrel. The design assumed certain acceleration profiles and barrel conditions. A short barrel and variable propellant loads sometimes challenged those assumptions. Underloaded rounds might not generate enough setback to arm the fuse properly. Overloaded rounds could cause violent acceleration and premature arming. Both problems appeared in rushed wartime ammunition batches. Reports occasionally described bombs exploding dangerously close to the muzzle. Training incidents began to shape the gun's reputation. Some barrels failed during routine live firing sessions. Of bursting and sending fragments into crews and observers, investigations linked these failures to metallurgical flaws and excess pressures. In other incidents, bombs exploded almost immediately after leaving the barrel. Here, fuse faults and over-energetic propellant charges were blamed. Word of these events travelled quickly through Home Guard units. For many, the Smith gun came to be seen as a weapon that might threaten its own crews as much as any enemy. Official responses came through circulars and revised procedures. Commands ordered extra proof firing of newly issued guns. Ammunition lots were to be inspected more rigorously, with suspect batches quarantined until laboratory analysis was complete. Where serious defects were suspected, replacement components were authorized. In practice, the volume of wartime administration caused delays, logistics chains moved slowly, and some units used older, unmodified guns and ammunition longer than intended. Accident patterns remained uneven from region to region. The character of the Home Guard influenced safety outcomes. Some detachments included engineers, machinists, and industrial workers who understood metal and machinery. They could spot a poor weld or a worrying crack. Other units consisted mostly of clerks, shopkeepers, and office staff with little experience of heavy equipment. No training program could fully erase those differences. Commanders relied on local initiative to identify risks and enforce good practice. The result was a patchwork safety culture that varied widely. Inside the ministry, the Smith gun became a doctrinal question. As some saw it as an emergency anti-tank gun and wanted it treated as such. Others argued it belonged in the category of heavy mortars. Classification affected ammunition scales, range access, and training priorities. If treated as artillery, it competed with regular units for time and resources. If treated as infantry support, its anti-tank role risked being sidelined. The paperwork shows this back and forth with no single view clearly dominant. In the field, commanders largely chose how best to use what they had. Industry had its own concerns. Factories making barrels needed predictable steel allocations and stable schedules. Rolling mills planned production months in advance. The War Office sometimes hinted at potential cancellations or reductions before decisions were final. And even tentative signals disrupted factory planning and production rhythm. Some firms began to see the Smith gun as a marginal contract compared with simpler, more stable orders. Negotiations over quantities, modifications and replacements could drag on, slowing the introduction of improved components. Mechanically, the Smith gun was unforgiving. The single grounded wheel was a critical structural point. If that wheel failed, the gun was unusable. There was no alternative baseplate or auxiliary stabilizer. Crews could not easily improvise a safe firing position if the rim was cracked or damaged. Under repeated recoil, a compromised rim might fail suddenly. Lesser damage could throw the barrel off true, skewing it relative to the horizon. Such misalignment introduced systematic errors into every range adjustment. So the elevation mechanism was a simple screw. The operator turned a handle to move the barrel up or down. Threads were exposed to dust, mud, and grit. Without lubrication, the mechanism became stiff and jerky. With too much oil or grease, threads collected abrasive particles and wore faster. Instructions recommended light oiling at intervals. Many home guard stores struggled to get standardized lubricants in sufficient quantities. Units sometimes used whatever oil they had, not all of it compatible with nearby rubber components. Traverse was achieved by rotating the entire weapon. The crew pivoted it on the grounded wheel. There was no geared system for fine corrections. The commander called for small adjustments, and the crew tried to inch the gun around using friction alone. On uneven ground, friction varied constantly. Fine changes often overshot or undershot the desired bearing. In live firing, this made it hard to hold a precise aim point. The sights were basic open sights with simple markings. No covers protected them when the gun was tipped or moved. Clumsy handling or hard groundings could bend or misalign them. Even small shifts had consequences at longer ranges. Home guard armourers rarely had sophisticated optical calibration tools. Many guns were used with sight alignment errors that were never fully measured. Crews tried to work around this by learning their own corrections in practice. In combat, with limited chances to test and adjust, that would have been much harder. Documents laid out standard emplacement patterns. Typical positions included hedgerows overlooking narrow lanes, farm entrances and small bridges. In towns, doorways, alley mouths, and gaps between buildings were recommended. The gun's low silhouette made sense in these constricted spaces, but tipping it onto one wheel required lateral room. Crews needed space to rotate it into firing stance. That movement could expose them at the moment they were most visible and least ready to fire. Transport by civilian car added further constraints. The gun's width had to fit between gate posts and long tight streets. Its wheel track could not exceed the narrowest common lanes. Its height in travel mode had to pass under archways and through farm entrances. Designers prioritized these limits over ideal firing platform geometry. The result was a compromise favoring mobility and storage at the expense of stability. Many emergency wartime projects reflected similar trade-offs. The Smith gun made them particularly obvious. The engineering drawings tell their own story. There are few complex curves. Most components are formed from straight lines and simple radii. Complex castings needing specialized foundry work were mostly avoided. Flanges are flat with straightforward bolt patterns. Joints use standard fastener sizes that workshops could obtain easily. This simplicity allowed manufacture to be spread across many facilities under pressure. It also left little room for incremental refinement without reworking the whole design. Any substantial change required formal reapproval from ordnance authorities. That meant proof trials, reports, and correspondence. Artillery ranges were crowded with more urgent equipment awaiting tests. Laboratories prioritized tanks, major guns, and core army systems. As suggested, improvements to the Smith gun often waited their turn. Only the most pressing issues, usually after accidents, were addressed quickly. Lesser problems lingered in production. Most guns in service stayed close to their original configuration. By the later war years, the Home Guard began receiving better alternatives. The PIAT offered a man-portable shape-charge weapon that needed no carriage. The 6-pounder anti-tank gun, more conventional and more capable, strengthened regular formations and key defences. These newer systems outperformed the Smith gun in penetration and tactical flexibility. In comparison, the older carriage weapon appeared increasingly obsolete. Planners reduced its role in future equipment tables, yet significant numbers remained stored in depots, raising questions about how best to dispose of them. But some Smith guns were relegated to training. They fired reduced charges on local ranges, using up older ammunition in a controlled way. Others were installed as static, last-resort weapons that might never fire in anger. Official documents rarely dwell on any combat use. Surviving reports suggest actual engagements were rare. Its lasting value lies more in what it shows about wartime procurement and engineering under pressure than in battlefield performance. Post-war evaluations adopted a cool tone. Ports acknowledged strengths, simple fabrication, low demand on CS resources, and suitability for modest workshops. They also listed weaknesses in detail, stability problems, safety issues, and the vulnerability of a single-wheel mount. Analysts highlighted the difficulties of tipping the gun under pressure. Taken together, these factors were judged to impose unacceptable risk on inexperienced crews. The Smith gun was classified as a stopgap. No serious proposal was made for further development or long-term retention. Looking back, the weapon fits clearly into early war, panic-driven engineering. Designers concentrated on what could be built quickly with available materials and tools. There was less time to study how the Home Guard would actually train with it. Metallurgical control suffered when production was spread across multiple firms. Safety margins shrank as production targets and quantity dominated discussion. Reports of early accidents took time to influence policy. Administrative inertia made it difficult to recall or retrofit suspect equipment quickly. The wider system worked under sustained pressure with little slack. Even so, the mechanical layout remains noteworthy. Using a wheel rim as both running gear and baseplate was unusual. It turned a mobility component into the main load-bearing foundation while firing. That choice reduced parts and saved material. It also exposed the same critical element to high stresses in two roles. Few later designs attempted anything similar. Most subsequent guns separated firing platform and wheels as a matter of principle. The Smith gun stands as an outlier rather than a precursor. The relationship between its smoothbore barrel and shape-charge ammunition also mattered. The absence of spin favoured the shape-charge's internal jet formation, but low muzzle velocity extended time of flight. That increased exposure to wind and small manufacturing imperfections. Crosswinds and minor asymmetries in fins or casting led to significant dispersion at range. Given already modest accuracy, this further shrank the realistic engagement envelope. To achieve results, crews had to let enemy vehicles come very close. At such distances, the balance between effectiveness and crew safety was uncomfortable. Archival material notes less visible costs. Noise levels were high, and effective hearing protection was rare for Home Guard volunteers. Blast over pressure affected crews near the muzzle, especially in confined positions. Medical officers recorded headaches and discomfort after extended firing. Long-term health effects never became a priority. No systematic studies were conducted. Storage conditions in small depots also took a toll. Many guns were kept in converted barns, garages, and/or outbuildings with poor environmental control. Humidity fluctuated, and condensation formed on cold steel. Barrels and breech mechanisms began to corrode internally. Before firing, crews or depot staff had to remove rust. If they did not, friction and pressure characteristics could change once a round was fired. Instructions on greasing and regular inspection were issued. Compliance depended on local leadership and volunteer time. Transport to this range could cause damage before firing ever began. Improvised towing arrangements attached Smith guns to whatever civilian vehicles were available. Some cars lacked proper towing points or rated hitches. Unbalanced loads strained axles and couplings. Under hard braking, the gun could swing and hit walls or posts. Such collisions bent wheels, twisted axles, or knocked guns out of alignment. Or workshops inspected damaged pieces when they were reported, but not every minor incident reached official channels. Photographs from the period show varied paint schemes. Some guns carried standard service green over primer, others bore rough hand-applied camouflage in irregular patches. Paint thickness affected how well surfaces resisted corrosion, especially on exposed metal. Areas frequently touched by hands and boots lost their coating quickly. These worn spots were touched up with whatever paint was available. Protection and appearance were inconsistent, but ballistic behaviour was unchanged. Spare parts created further complications. Distributed manufacture made it harder to standardise every dimension and part number. Small production variations meant components were not always fully interchangeable. Spare wheels might not fit hubs without adjustment. Replacement breech parts sometimes required hand-fitting by armourers. Documentation tried to define tolerances for critical pieces, but practice remained imperfect. Local stores often cannibalised unserviceable guns to keep others running. Over time, this preserved some weapons while reducing overall numbers. Training manuals were formal and diagram-heavy. They showed tipping sequences, crew positions, and ideal stances. Text stressed safe distances and clear arcs of fire. But static diagrams could not fully convey shifting balance or awkward handling on uneven ground. Only repeated practice taught crews the real effort involved. Soft soil, steep banks, or rutted tracks changed the gun's behaviour sharply. Printed guidance infinitely lagged behind the human experience. The Smith gun remained largely a domestic weapon. It was not widely exported. A few examples may have gone to certain Commonwealth Home Defence units, but its core users were British. This kept most feedback within British channels. Reports had to move through several layers of command and administration. Along the way, some technical detail was lost. As a result, recurring mechanical problems did not always appear clearly at the top. Financially, the weapon initially looked reasonable. Unit costs were lower than full-sized anti-tank guns. Tooling investments were modest, and many factories could slot components into existing workflows. The absence of complex recoil systems and optics kept costs down. Accounting figures showed efficient use of money and material. Later accident investigations did not always include wider costs, injuries, and lost training time and pressure on medical services. Those remained largely uncounted. Morale in the Home Guard was influenced by what the gun represented. On paper, it signalled that the authorities were taking their role seriously by issuing a heavy weapon. Receiving it could feel like recognition. But as accident stories spread, confidence eroded in some units. Crews wondered whether it posed more danger to them than to enemy tanks. Instructors tried to counter those fears with controlled firing demonstrations. When these went well, doubts eased somewhat. When they did not, skepticism hardened and was difficult to reverse. After the war, the Smith gun disappeared from active inventory. Some were scrapped and melted down, others went into private collections or remained as training curiosities. Though museums eventually acquired a few examples. In displays, curators pointed out the unusual carriage, the pram-like silhouette, and the context of its creation. Placed beside more conventional anti-tank guns and mortars, the Smith gun stands out as a product of early wartime Britain under threat and short of options. Today it serves more as a way to discuss decisions made under pressure than as a weapon in its own right. Modern engineering tools applied to the design would likely confirm established experience. Computer models could map stress patterns in the axle. Simulations could show how the rim deformed under repeated recoil. They would highlight stress concentrations around welds and bolt holes and progressive deformation where the wheel met the ground. None of this would change the historical verdict. Yet it would simply restate earlier observations in contemporary analytical terms. Viewed as a system, the Smith gun is internally consistent. Its features reflect a clear design philosophy. Build something quickly from what is available and get it into service. Each simplification follows from a real constraint in material, machinery, or time. None of its compromises are random, but internal consistency does not guarantee safety, effectiveness, or acceptance. The Smith gun filled equipment tables more readily than it met the needs of crews. It entered the records faster than it proved itself on ranges. That gap between administrative success and operational performance is a large part of why it remains interesting. Its unofficial nickname came from its silhouette, to many who saw it, though the gun looked like a baby carriage turned into a weapon. The image captured the contrast between appearance and purpose. The nickname, however, changes nothing about how it worked. Dimensions, wheel spacing, and barrel length are fixed, measurable facts. Evaluated on those terms, conclusions remain the same: structural compromises, narrow safety margins, and strict limits on its safe tactical use. Even guns that never burst or failed dramatically could misfire. When they did, crews had to follow a careful drill to avoid delayed detonation. They waited, approached, and extracted the bomb according to procedure. All of this required calm, stepwise behaviour, possibly under enemy observation. Local attempts to simplify the drill sometimes introduced new risks. Later amendments tried to standardise misfire responses. And how quickly those changes took effect depended on paperwork, training capacity, and wartime communication. In the end, the Smith gun represents a layered response to a particular moment in Britain's history. It was built to plug an immediate gap, not to serve as a long-term cornerstone of defence. It used materials, workshops, and skills available when more ambitious projects might have produced nothing quickly. Its flaws, mechanical, doctrinal, and organisational, grew from compressed development and limited testing. Its story survives in reports, surviving weapons, and the recollections of those who trained with it. Together, these sources allow reconstruction of the decisions behind it and their consequences. As a case study, it shows how technical compromise, once accepted under pressure, can echo through an organisation from the drawing office to the men standing behind the gun.